number 50. This is on practice midterm number 3. This is the last of the true-false multiple choice comprehensive questions that you'll be filling out on the Scantron. The question is, use the following bond dissociation enthalpies, and I have delta H, oxygen-oxygen double bond is 498 kilojoules per mole. Delta H for the hydrogen-hydrogen single bond, there is no other, is 436 kilojoules per mole. And the delta H, or the enthalpy of the oxygen-hydrogen single bond, is 464 kilojoules per mole. And use that to predict the enthalpy of the following reaction. And this is the familiar one from the Hindenburg or the Challenger, whichever you choose. But I take 2 hydrogens plus 1 oxygen, and I'm producing 2 water molecules as a product. And so I give the following possible answers. A, minus 486 kilojoules per mole. B, plus 486 kilojoules per mole. C, minus 442 kilojoules per mole. D, plus 442 kilojoules per mole. And E, 1856 kilojoules per mole. So this is assumed to be positive, unless otherwise noted. And so it's a simple matter to do this. We're going to have to do the calculation, and so you'll have to work this one out on scratch paper. And in order to do that, you're going to follow the following sequence, the same as we used with the in the written part of the test. We're going to write the reaction out using Lewis dot structures, and so I have 2 hydrogen, or hydrogen-hydrogen single bond, plus oxygen, which is double bonded to another oxygen, dioxygen molecule, is going to give me 2 water molecules, with a hydrogen bonded singly to an oxygen, which is bonded to an equivalent hydrogen, so I have 2 H2Os. And what we have to ask first is what bonds have to be broken and which bonds have to be made in order for this process to occur. And in this case, it's all of them. And sometimes there's a simplification if some bonds aren't broken or made, but in this case, we're going to have to break them all. So I'm going to have to come along and put energy in to break this hydrogen-hydrogen bond. All bond dissociation energy enthalpies are positive because you have to do work to break the bond. So I'm going to have to break this hydrogen-hydrogen bond. I'm going to have to break this oxygen-oxygen double bond. And then these are going to be endothermic. So I'm going to have to add the bond dissociation enthalpies. And then I'm going to produce 2 water molecules, in which case I'm going to have to form for each water molecule, I'm going to form 2 hydrogen-oxygen single bonds. And so this is going to be bond forming, and bond forming is going to be one that's going to release energy. When the energy that had to be placed in to separate the bonds is going to be released when the bonds form. So this is an exothermic process, bond formation. It's an endothermic process for the bond dissociation. And now it's a simple matter of bookkeeping. So I'm going to write it out on my scratch paper the way I would in my written parts so I can keep track of my logic. So I'm going to have 2 moles of hydrogen, and there is 1 mole of hydrogen-hydrogen bonds for every 1 mole of hydrogen molecule. And the bond dissociation energy for a hydrogen-hydrogen bond is 436 kilojoules for every 1 mole of HH. hydrogen dissociation plus 1 mole of oxygen, taking the stoichiometry into account, of O2, and there is 1 mole of oxygen double bond for every 1 mole of O2. And dissociation enthalpy for O2, oxygen double bond is 498 kilojoules for every 1 mole of oxygen double bond. So that part is positive because this is bond dissociation. I'm going to break these apart. How much work do I have to perform to pull these apart and break the bond? Minus, now I have 2 moles of water, H2O. There are 2 moles of oxygen-hydrogen bond for every 1 mole of H2O. And there is 464 kilojoules for every 1 mole of oxygen-hydrogen bond dissociation. And that's it, because there's only one product. So the stoichiometry is taken care of. The number of bonds in the molecule that are being broken or made are taken care of. And the dissociation energy is all written out. And not that this is going to help you on a filling in the bubble, but it will certainly help you keep track of your bookkeeping. So what I have to do mathematically now on my scratch paper is multiply 2 times 436, which is 12, 6, 7, 4 times 2 is 872, plus 1 times 498, so I have 872 plus 498 is going to give me 10, 17, 9 and 4 is 1370. So that means it's going to give me 1,370 kilojoules per mole minus, and now I've got 2 times 2 is 4. 4 times 464, so 464 times 4. 4 times 4 is 16, 6 times 4 is 24 is 25, 4 times 4 is 16, and 2 is 18. 1856 minus 1856 kilojoules per mole. Now I simply do the math. 1370, that's a 6. 15 subtract 7 is 8, and that would be 7 subtract is 486, and it's going to be negative. So this is equal to minus 486 kilojoules per mole. So now on my scratch paper I've worked it all out, which option minus 486. Well, it turns out to be option A. So I would, on my Scantron, fill in the bubble for A. So it's simply filling in the bubble on the test. This is what you're going to be doing on the scratch paper. There will be a question like this. What?
A on the paper too.
Oh yes, I'll also fill in an A on the page for a hard copy backup on your test. I advise doing that way in case there's a problem with the Scantron, we can go back and see what happened.